Always good. This is a natural for you.
Sure. It's so not. Hi, everyone. Oh, shoot. I hit the wrong thing. Awesome. Oh, there we go. Okay. Hi, everyone. Welcome back to Learning Space. We apologize. We've had to miss a couple weeks. We've had travel and sick and grant writing. Last Wednesday was pretty intense, actually. Yeah, we were sitting in this room going type for an NSF deadline. So thank you guys for your patience and your support and your comments and messages and your understanding when we have to cancel last minute, even a couple weeks in a row. So thank you guys out there watching. Hi and welcome. Yes, we're in George's office today because my computer decided to completely flip out this morning, and so right now it's restoring from backup next door. So thank you, Georgia, for letting me take over.
Anytime.
Come in a frenzy and take over your computer. So with that introduction, we have a special guest with us, Sandlin Buxner. Welcome from University of Arizona.
Thank you.
Hey, Sandlin is a good friend of ours, colleague of ours. Does amazing work in science education research, in teacher professional development, and probably a whole bunch of other things that I can't even think of off the top of my head at the moment, but that's the kind of stuff that we've worked on with you before. And I want to say hi to everybody. If you're watching this live, you can join the comments. We've already got comments for the, I'm trying to read Nancy's comment. Oh, because it has a link in it. So using the Q&A app, if you look over here somewhere, it says click to join the Q&A. That lets you leave us comments and questions. And Michael says hi. And Nancy's in there. And I saw a couple of you guys. I apologize also for setting the wrong date for this. A whole bunch of people thought it was yesterday because I failed at date and calendars. No, it's all worked out. It all worked out. That's what matters. So thank you guys for coming along. Be sure to ask any questions throughout our discussion. So, Sandlin, we invited you because we wanted to talk some about your research into science literacy. Can you start with a definition of science literacy? And then, yeah, I know, it's like a big topic, but I want no pressure. No pressure.
No pressure. No. So. Thank you for having me on. I am Sandlin Buxner. I'm at the University of Arizona, and I work in a Department of Teaching, Learning, and Sociocultural Studies, but I also work in the Department of Astronomy, where I work with a professor, Chris Impey, and we have some wonderful undergrads who work with us, and we have been conducting studies of science literacy. And so one of the things that when we go and talk about this with researchers is we have to define what it is we're talking about. And for anyone who's ever read the newspaper, we throw the word around a lot. We say that science literacy is important to the American public, and it's more important to children, and it's important to not, the Ebola outbreak is all about science literacy. And even I work a lot with NASA, and NASA administrators say that science literacy is really important. But when you really try and press on what science literacy is, people start to break down because it's really hard. And so we get a lot of fuzzy ideas like, I want them to know things in science, or I want them to know how to do science, or I want them to have scientific thinking. And the person that a lot of us look to is John Miller. And John Miller is the person who was commissioned by the National Science Board, NSF, in the 70s to start looking at public science literacy. And he and a colleague started the Science and Engineering Indicators of the Public, and they started asking questions. And back in the day, right, back when we were all children, the kinds of questions were really basic questions. And so I have a graph, actually, that will help you understand the types of questions I'm talking about. So just on slide 1, these are facts, right? Declarative knowledge of things that they thought, gosh, if people knew the answer to these things, maybe they had a baseline of knowledge. And you may actually recognize them because, when you're on Facebook and things, Pew Research will say, are you scientifically literate? And a lot of these questions overlap. And so, things like right now, this might be really important, right? Antibiotics kill viruses as well as bacteria. Yeah. And it's one of those things where we want people to go, no, antibiotics are only good for bacteria, but not things like, oh, I don't know, Ebola. Right. There are some, controversial type questions like humans evolved from an earlier species of animals. This, of course, is controversial if you don't believe in evolution, but is something that people really thought, gosh, if you'd gone to high school and really paid attention, you would know this. Plate tectonics, less controversial, although some. Then some more difficult questions like all radioactivity is man-made. Having people understand that it's not just a man-made problem, that there are a lot of radioactive materials that are good and natural, and if you took chemistry, you would understand this. This one was in the news about a month ago. The Earth goes around the sun. Going back to, do people actually understand that we are not an Earth-centric universe? And even though probably all of my college students truly believe that, they don't care, right? That they are the center of the universe. And truly understanding just basics of celestial mechanics and planetary motion and going, gosh, the sun is actually in the center of our solar system, but not the center of the universe. And certainly the Earth goes around other things. The one that became really problematic is the second from the bottom, which is astrology is not at all scientific. This became really problematic for something we call a validity reason, that it was unclear from this question whether people understood the word astrology, if they truly meant, their horoscope, or if they were, all the others are ologies, biology, geology. So, even very well educated people call astronomy astrology. So this one got tossed. But back in the 80s, this was one of the predictors. If you didn't get this one right, you weren't considered scientifically literate. And they had to eliminate it when we really started looking at measurement issues. And then the last one.
There's two letters different, right? I mean,
exactly, it's the same thing. I've had PhDs go, you're an astrologist, right?
Right.
And so we have to get at that in different ways, and some of the ways we've gotten at that, instead of asking about the word astrology, is we go, do you believe the motion of the planets affects your daily life? And all of that. And so, so going back to what is science literacy, some people will define it as just some basic knowledge, right? The second piece that John Miller had started to look at was, could you describe what it meant to study something scientifically? And the way they do these surveys is they call people. So sometimes you'll get called. They call about 2,000 people a year, maybe every 2 years. And they'll just start talking to you, and they'll say, well, what do you think it means to study something scientifically? And they have this list of things they want to hear from you, right? Rigor, controls, and so they had a list. But the issue is scientific literacy, and there's a whole chapter for the big education nerds in the handbook of science education. It's on my.
Have it?
Oh wait, let's see. I have it right here.
We were using it last week. Oh wait, there it is.
Oh, it's so big. It's this enormous book.
Oh, she's got the paperback.
So this, just off the presses, the research on science education.
This was Wednesday.
There's actually an entire chapter that is scientific literacy, science literacy, and it's just a big issue. And so it comes down to, we're not talking about the knowledge of how to be a scientist. We're not even talking about, we're just talking about, the way John always described it was, could you have enough background knowledge to read back when the New York Times had the science page? Right? And, it was understanding, can you maybe do some graph reading and just be a really informed consumer? And that's really how we start to think about it is, maybe not the most popular view, but there are some declarative knowledge things, which is why we still ask questions like, does the Earth go around the sun, or does the sun go around the Earth? Can you just have some basic declarative knowledge? We do ask students to answer the question, what does it mean to study something scientifically? And we look at both the quality of the response and the types of things that they say. One thing that's really interesting for anyone who's been a teacher is we know that students are really good at regurgitating words.
Yes.
Like they'll say experiment, hypothesis, control, but we don't know how they're using them, right? So, but they're really good, and they're like, I remember the they'll say scientific method. And so we do all sorts of analyses to say, are the right words there? So that's like a word count analysis. Then we start looking at how do they put the words. We call it a quality analysis, and I'll show you some data from that. And then third is we go into the literature on scientific inquiry and the nature of science. And there are a few research groups. Norm Lederman leads a really famous group that looks a lot at this, and Renee Schwartz, and we go and code. And just to give you an idea, we've looked at almost 12,000 undergraduate students at the University of Arizona over 25 years. I was not here when it started, but we have done it. And so if you can imagine reading 12,000 of these and coding, and we have about 50 codes that we go through, and so we might say, do they understand the empirical nature of science? Do they say, or do they have a very objective view where they say we want to prove things? It's all about facts and truth. And so we code them out, and we really start to get a good feel for what we think is their baseline science knowledge. Now, in a perfect world, we'd sit down and interview them, each and every one of them, for half an hour, but we can't. And so we really are in an assessment issue. And so going back, we call science literacy, in our view, it is this baseline knowledge that we want for our citizens to understand knowledge, like when they see something scary and they don't know, did that come from The Onion or did that come from the New York Times, to be able to sit back before they call their mom and say the world is about to end, right? That they have a little bit of time to reflect and go, is that reasonable? Is that in line with what we know about the world? And I think right now people are really worried with Ebola, with climate change. Can you be a participant in the discussion and be well informed? And may not know the answers, but really be able to, again, not panic, because these are things that are starting to edge into their life. I'd say many of the issues people just don't care about, including climate change. But it's one of those things where we want people to have informed decisions, make good choices about their medical care, make good choices about their children. And so that's what we're considering to be science literacy. But I will tell you that you could put 5 of us in here in a room and we could argue all day about it. And sometimes it just comes down to a measurement issue, because in research, just like all science research is, we have to have our definition set before we can go and measure it. And so that's the type of definition we are going with when I show you all the measurements. They really are based on how we think about science literacy.
Sure. I think I'm glad you brought up Ebola, because, of course, we've been hearing a lot more about Ebola, even though it's been going on for several months in West Africa. We're hearing a lot more about it in the U.S. now, after there have been several cases, and it's become a huge political issue, and really a policy, not political, but a policy issue, is what to do with healthcare workers coming back. And so people are making decisions without all the scientific knowledge, or making, so you have the CDC, which has years of experience saying one thing, you have certain governors saying other things, and so yeah, I think that really brings it to light very starkly for us, is the issue of science literacy and everyday decision making.
Yeah. And I think, I work at a university, and one of the things in our non-major population, and the thing we like to throw around a lot, is whatever your favorite non-major class they're taking is the last science class most people will ever take in their life, right? That's it. And so we always talk to our instructors and go, what is it that you want to get across to these students in the last time you see them? Is it a whole bunch of facts, right? Is it inspiration? Do you want to impact their reasoning? So, yeah.
So that first graph that we showed, you've got kind of 3 different populations. Do you want to talk a little bit about?
Sure, I'd be happy to.
What you mean by NSF, and then UA is University of Arizona, Gen Ed versus freshmen.
Yeah, so what we did on this is, originally we had written a paper that's been published in the Journal of College Science Teaching, and that's where this graph comes from. And what we were trying to do is we're trying to figure out really what the predictors for science literacy were. And so John Miller in 2004 had said he thought the best predictor was Gen Ed, and everybody got really excited, and we said, well, great, we can test this, because we have a Gen Ed population.
That's a willing population. They'll do the credit.
Yeah, and just to let you know how we do these surveys, they're still paper and pencil, so they all get transcribed, and we do it, the first couple days of class. And we don't care, we don't collect names, so we get thousands of these every year. And in this graph, what we did is we went through the science and engineering indicator data. If you ever want to dig into it, is public domain. You can order it from NSF. You can also get to it on the website, but you can get all their raw data off their little CD they have for you. And that's what we did. And this is as best they can do, a random sample of the U.S. population of adults over 18. And it tells of their percentage aggregate how many of those individuals were getting each of these items right. Like, what's the percentage? So we'd say that, the Earth goes around the sun, if we look in the U.S. population, almost 80% of respondents got that right. And what we noticed is we broke our population into our freshmen, so students who are basically high school plus 3 months.
Mm-hmm.
And then we broke it into our gen ed. So University of Arizona, very similar to many large state universities, has some type of science requirement. We started this in 1998. And so we wanted to test it and go, gosh, does having 2 random classes in science make you more scientifically literate on these questions? And interestingly enough, you can look that, yep, first off, going to college, self-selecting yourself to college already does it, right? You perform better than the U.S. population on all except for that astrology question.
Right.
Whatever, we actually don't use it anymore. But having the gen ed class ekes you up a tiny little bit. And just to let you know, what we do with this data is we actually will run statistics on it, on our large samples. And we have modeled this. And one of the things we do is we give you a science literacy score, a quantitative score. How many of these items out of 15, there are 15 that we use, did you get right? And interestingly enough, we have a little covariance, but the 2 factors are your year in school and how many college science courses you've taken. And everybody rejoices and goes, yay! Except when you look at the actual effect size, which is about, everything altogether is about 4% of the variance. So we go, gosh, we improved our science literacy and we can account for 4% of the variance based off of them taking more science classes. So yeah, it's statistically significant, but it's not really a meaningful thing. Right, and so it's kind of made us go, what really does contribute to these students' science literacy?
Mm-hmm.
The other thing I'll have you show the second
Sure.
graph in here. And so one of the things that people have been asking us also is they go, gosh, you guys have been doing this for a really long time, 25 years. So we've been collecting data. And one of the things that we've shown is that there's actually, if you look across the board, no statistically significant change. It is so flat.
So these are
right.
years.
Yeah, so we always have a mean right around 70%, about 10.3 out of our 15 questions.
Okay.
Super flat. And it's flat from the 80s, the 90s, 2000 to now.
Wow.
Now, we do have some freakish years where we had like just all science, right? We have to account for a lot of these kind of idiosyncratic variabilities in the data collection, right? We may have just grabbed a more science heavy class. So we have to kind of balance that all out. But what we were showing is we really don't see a change. Interestingly enough, only 3% of students out of almost 12,000 have gotten all the questions right. I was very excited. After doing this research, I got to go to the Pew Research site, and I managed to get all the questions right. So excited. I can't remember what they told me where I was in the population, but I was very excited to be on the tail. But the thing that we find really interesting, and I'm not sure how readable it is, I apologize, is if you look, we also break it down by our colleges. And so all the way on the left, you can see what are declared. These are, kids who haven't declared a major, have told us, this is self-report, by the way, because we don't have their records. Mm-hmm. I don't know what I want to do yet. And you'll see that they hover right around 11 out of 15. Nobody's surprised, but our science and engineering, the next 2, do the best. And we go, great, self-reported majors. We're not really sure why they're in intro science classes for non-majors, but they are. They do the best. Then we kind of go through our colleges, and what kind of makes us bummed out and we're really surprised about is our education. So these are usually our pre-elementary teachers do the worst. Mm-hmm. Worse than our undeclared. Mm-hmm. Always bummed, and that is consistent every year. And the thing that always makes me a little scared, although it's a pretty low end, is our pre-nursing, pre-med students.
Wow.
But I will say there's only 125 of them, so, that may not be as reliable. The one that I always like is the ones who really just are indicative of our sample are our business, law students, architecture, and fine arts. And those are the ones on the right, and they're hovering right around 11. And they're kind of the quintessential student in this class. There's a lot of them, and they're pretty stable and reliable. And their knowledge doesn't change. And so that's what we start to say, what major they were in had a very low predictability. right? So we could see science and engineering, that did pretty well. But then I'll have you go to the next slide, because this is the last thing we looked at. We started to look at their beliefs. We thought, aha, would we look at their beliefs to see if that made a difference? And lo and behold, so how do we get this data? Well, it's interesting. On the back side, we asked a bunch of Likert scale questions. And so Likert scale are those ones where they ask you a statement. And then they say, do you strongly agree, are you neutral, all the way to strongly disagree. So on this was a 5-point scale. And the questions, we have 24 of these questions. And they're statements like, you know, I believe in lucky numbers, or I use psychics, or things like that. So they're fairly straightforward questions. I believe that the movement of the planets affects my daily life. And what we did is we did a large study. We had so many students to work with. We got to do this really cool thing. We got to do an exploratory factor analysis and then a confirmatory factor analysis. And we came out with 5 factors. But what we found most interesting were these 3 factors. And so the first one is belief in life on other planets. This is not the wacky, I have been visited by aliens, but this is truly, right? Do you believe that life could exist on other planets in the astrobiology sense?
Mm-hmm.
And so you'll see there's not really a big difference between the science literacy score, excuse me. So on the left are people who agreed that there could be life on other planets versus disagree. There's not really a big difference between our strongly agree and strongly disagree. Now, this does, you'll notice the number of participants goes down. I excluded everybody who was just right? Mm-hmm. So you actually had to be really far. You had to have a factor score of all these questions that was really high, above a 4 or below a 2. And so everybody who was kind of wishy-washy or answered randomly got kind of dumped from this analysis. But then the next 2 are really fascinating. So the faith-based beliefs, right? Do you believe in, excuse me while I make sure my battery is on before I lose you all. Okay, there we go. Those who had faith-based beliefs, so very biblical beliefs, and it was you know, very overt, so we weren't beating around the bush. Their science literacy scores were substantially different, like 2 points, right? So I mean, when we say substantially, it was the difference between being an education major and being like an engineering major, right? But it still was a really good predictor, and you can see we have a pretty even sample size. And then our other good favorite one, which was in the middle, was belief in unscientific phenomenon. So those would be things like lucky numbers and whatnot. And so, interestingly enough, their beliefs, how they responded, self-reported, started to account for, you know, now we're getting into like 20% of the variance, which makes a lot of sense because your beliefs often describe things like, do you believe that humans evolved from earlier species? So that's the kind of work that we've been doing in science literacy, is really taking a look at patterns. What I don't have in these graphs is we have a lot of our students going through, there were 4 open-ended questions, and painstakingly going through and coding what does it mean to study something scientifically. So I have a student who will be presenting her work here at the Division of Planetary Science meeting in 2 weeks on that. So she'll have a poster on that. And then I have a student who's about to release an article on what is radioactivity, which has been really interesting. Especially with some of the recent things about how many people have a fear-based response to radioactivity. You know, and so that had been really interesting. So he did some trend analysis to say, when we look at national, international incidents like we had in Japan, do people's responses change? And so it's great that we have hundreds of responses each year to look at some time trends. Again, we always have to be careful of who's in that class, who's answering it, and not make really strong inferences, but it has been really interesting just to look across the board. How do our STEM majors versus non-STEM majors answer those types of questions? You know, are they understanding in astronomy class that we're talking maybe about the electromagnetic spectrum? Things like that. So it's been good fun. And then we do have a question about computer software, which has been very interesting, especially looking over 25 years, how that changes. And then our last question is all about DNA, and so we do have another student who is preparing a manuscript on students' responses about DNA. We did just do a comparison, so our students are non-majors, and we just got a sample of our introductory molecular biology majors here to see if they understood the true difference, right? And the thing, when we talk to biology educators, that they're really interested in is this idea of heritability. It doesn't matter what it looks like, although lots of people will tell you. But it really matters is that's the stuff that gets passed down that makes us who we are. And it's been really interesting to look at that. And so we spend a lot of our day looking through all this data, collecting, of course, constantly collecting more data, and seeing what types of analyses we can use to help us understand our undergraduates. We're really careful to, of course, talk about our undergraduate sample and not infer to the entire population, although lots of people like to use our data in that way.
Right. Actually, there's a related question from Nancy Graziano. Is there a way for the general public to participate in these kinds of surveys? Or maybe you can talk a little bit about how the NSF did their general survey.
Sure. And so in the university studies, we'd always love for people to come in off the street, but of course, the human subjects is where we get ourselves into trouble. When you look at doing these types of studies, often what companies are doing, and so Pew does this, I've seen from different companies, is they'll crowdsource it. And so when you see a link online saying do you want to answer this question, you're actually kind of consenting to being involved in that data. For NSF, you can't just volunteer. It's not like one of those psychology studies. They do their random samples, and so you can't just opt in. And so the best way is really to kind of see, and they're really good about advertising on Facebook and places like that to say, hey, do you want to answer some questions? And then you become part of that crowdsource, part of that data.
Okay. We have a question from Elad Avron asking, what are the stats regarding gender gaps in science literacy? His anecdotal experience shows that it's improved greatly, but that what's the trend? What's the deal with gender in science literacy?
So, in general, we know that unfortunately women have done poor in the past. In our particular sample, women underperform, but only by a tiny bit. And so it shows up in the data because we have so many, but we're talking about just about 2 percentage points. And so it doesn't make us nervous at all. And so we are happy to say that in our particular sample of data, it's not a predictive at all. So we see it, but it's not enough that we go, oh, one gender is underperforming. And I would say, in a lot of ways, and I know we're all on these groups where we start to look at all different types of diversity, that, we have more female PhDs. I mean, all these indicators in society are showing that women are catching up to men intellectually, maybe not financially, but intellectually that women have caught up. What I think we're all really concerned about is students. And so at the university level, I think we don't see it. I don't do a lot of research with K-12, but when I talk to my colleagues, that, of course, is where that gender gap lies, especially starting in middle school. And so when I go to conferences and talk to people, that's where we're most concerned, is with our middle school girls and boys, right? I mean, we're concerned about both, but kind of evening it out. Because, of course, that's the other discussion we get into is we would not want to disadvantage the other gender. Right. We are just trying to pull our girls up and really looking at, does that look like single gender education? Right? What does that look like? Is it what teachers say to them? And so, like I said, that's unfortunately not research that I do, but I do talk to a lot of colleagues who are very interested in that. But that's a great question.
I'm curious what you could, okay, so I went to an all-girl high school that had a very strong science program. So I'm curious, has that shown to have an effect, to have single-sex education or single-gender?
No, I'm not sure. I haven't read any studies on it, but I've seen mixed on that. But interestingly enough, single-sex education has been one way to combat a lot of that. But I think you run into other problems too, as I talk to lots of teenagers about having to be stuck in the single-sex school. So.
Girls are awful.
There's no solution.
Yeah, it's definitely not a perfect solution.
Yeah. So do you share this, I'm sure you do, with the colleagues that you work with or the colleagues at your university, and how do professors who teach the science courses, how do they respond to this? What do they think of it, and what do they think of, I guess, science literacy as you've sort of defined it?
Yeah, and so, we do share it, and one of the most basic ways we share it is because we have to, right, I don't teach in that part of the program, and so I'm constantly asking professors for their students, right, because I want to recruit them.
Yeah.
Right, and we do share with our colleagues, and, it's very mixed. there have been a lot people who are really versed in the astronomy ed world know that, you know, over the last 20 years we've been trying to figure out, like, what is the basic intro Astro 101 curriculum.
Yeah.
Right, I had a colleague, Eric Brodt, who part of his dissertation was trying to figure this out, right? Like, what do we care about? And it doesn't matter. We've done plenty of studies in AER to go, what do you guys think we should do? And we all go to conferences and talk about it. And I think we finally decided about 10 years ago it's not even worth us fighting about it because, right. And so the issue is there's kind of a couple different camps. There's the camps of they must understand Newton's laws and Kepler and all of these things. And so they're probably not the science literacy folks. But then you have a lot of the people, I have a great colleague here, Don McCarthy, who is very famous because he runs astronomy camp. And people like Don really value science literacy, and the type of literacy they're actually interested in even more. So he's been working with a graduate student on something called quantitative literacy, or numeracy. Mm-hmm. She just defended her dissertation last week. We're very excited, Kate Follett. And she's very specifically interested in the quantitative literacy of, can people even like read a graph or a table? And, you know, we have discussions, and it's like people who do have quantitative literacy, it correlates very highly to scientific literacy. Mm-hmm. And so that's the thing that we see is when they do well in school, they do well in school. And I think that is something we know really well, that good predictors are GPAs are really good predictors, things where we know that students are paying attention and care. But so we do share out internally within the university. Of course, we also go to conferences where we have colleagues, not just in astronomy. We share it with colleagues in geology and planetary science and chemistry and biology. And then, you know, we publish in places like the Journal of College Science Teaching, Journal of Geoscience Education, places like that where we think they'll be interested colleagues. And we definitely talk about it and collaborate. And so we do have some other universities who like to collect data, and we compare results and see how things are going. I will say, if anyone's interested in just using some of the questions or using the survey, we do have it in the Journal of College Science Teaching, and I can send you a link. Part of this work was funded by a Tier 3 NSF grant, and so these papers are up, and anyone can get to. I know that if you're not a university, getting university access is quite miserable, but what I'll do is I will send Nicole a link. Sure. So that if you just were curious enough to read a couple articles or even just one article, it's on the CATS, which is the Collaboration of Astronomy Teaching Scholars website. And I will send her a link right now. And while you're there, you can always see what other great articles are there. And so you can see a lot of the work our colleagues do in lots of areas, kind of in the Astro 101. And so let me just, I bet I could put it in here. Let's see if I can put it into the...
Yeah, there's a chat function over on the left that you could put it into, and I can grab the link from there.
Perfect. So here's the link. And so like I said, so that way it's in the access where you can get it without being behind a journal.
I'm going to put that in Showcase, and I will remind you guys of the Twitter trick. Use the hashtag ICanHasPDF. Yes, that is lolcat speak. Usually somebody will come through for you and who has university access. There we go. Show item. It is yes. It is questionable for several reasons. However, I will say it is useful.
It can work.
It works, especially when I'm A, off campus, or B, it's a
I didn't know that.
An article that we don't have.
Yeah.
Some very helpful Twitter followers. So that is a possibility if you're not at a university. We had some comments on theory and hypothesis and fact and how that gets confused amongst different populations from the general public. To do you have anything that looks specifically at that kind of part of science?
So that's in all of our open-ended, but I think that that's a really great point, right? So one of the things I do a lot of work on, or I had when my dissertation was, I looked at the very academic, nitty-gritty, almost boring, painful part of the nature of science. And if you look at that, right, people get very upset about how we use the word law and theory and guess and educated guess, and there are a lot of people who care a lot about it. In this kind of work, we try and get away from making too much of those words. And so we do note when they say law or theory or guess, but we don't make really strong inferences about that because of that. And we truly believe, you know, when we think about what it means to say something scientifically, that we're hoping that people will talk about questions and evidence. Evidence is really big for us, right? Experiments don't have to be, especially in astronomy. And I think that, you know, you're in one of two camps when it comes to all of that. You're either you care and you say language matters and it matters what people say, or you go, we're really going to look at how we think students are using it. Because I have a lot of colleagues who have problems with the word prove, right? How many times were you in your intro science class and your TA crossed out and said, we only disprove things, we cannot prove things.
Right.
But scientists use the word prove all the time in a very colloquial way. Like, I know if I use the word prove, I try not to now that I've, you know.
Yeah, now you're aware. Yeah.
But we use the word prove in a very different way. And again, it comes down to the epistemology of how are we thinking about it. So I think that's a really great point. And I will say, when they do studies of even like PhD scientists and all those words, some of them, quote, get it wrong. Right, and so when we talk about it, we have to be careful, like, what's our purpose here? And so I think that is just a really great point. And so, like I said, we do note it for our accounting purposes, but we don't make strong claims about theory and law, for sure, and hypothesis.
But that may be something that should be focused on for the science communicator community.
Absolutely, I think
they're the ones who are understanding it, science educators and communicators.
And I think, unfortunately, that means the burden is on all of you to be very careful about the words that come out of your mouth, right? To use it well, but not to condemn all of our friends who ask a question, right? How many have seen the poor person in the public talk use the incorrect word and then be very snappily, you know, corrected by the scientist?
I've seen that happen, and I'm not even going to say who snapped at the poor audience member who was brave enough to ask a question. Yes.
Oh, all right.
But I was there, and that's terrible, because I was just you're making me think of, you know, people's attitudes towards science and what they think it's good for, and there's sort of almost a cultural aspect to all this too. There's this culture of science, and if you think you are a part of that group or not. And when we think of public literacy, of course, we're hoping that people will use scientific reasoning and to make these important decisions. But if you don't even feel like science has anything to offer you, or if your attitude toward it is so terrible, like it's so elitist, or it just doesn't have anything to do with me, then how are you going to even bridge that gap to use scientific reasoning and be literate, however you want to define it? So, yeah, you do have to be really careful. Yes, the communicators, the people that interact with the public, who are that public face of science, that's really critical.
Yeah, and I think, you know, one of the things we have to be very careful about, and I find in my research that I need to be very careful about, is that, you know, in no way do our results show that our students are scientifically illiterate. And I really try and stay away from that illiterate word, because, again, we are setting a criteria out and saying, okay, right, this is a criteria, how do people do? And again, we're looking at a large population. But we want to look at all sorts of things, like, do they like science? Will they engage in science? So actually, this is a nice segue, Georgia, into some other data we've collected. One of the other things we did in the next study, we got another NSF grant to do, was to really start to figure out, where do people get information about science?
I love this.
Yeah, and we iterated on it, you know, and we first started by just asking people, like, I had 700 open-ended questions. I was like, where do you go? And we got really good feedback from other scholars and people who said, well, it really matters what the purpose is. Are they doing it for class? Are they doing it for their own knowledge? And so I have two graphs here, which I'll have you show, which actually, they look similar, but I'll tell you the difference. And so if you go to slide 4 in here.
Okay, I'll get that up.
And so again, we've collected data for a couple years now. We have a couple thousand sources on here, so I don't have an N on here. But this was, I presented this last year at the AAS, but this was saying the top sources. And so the difference between this, we basically say, like, where do you go first? And then where do you get most of your information? This is the where do you get most of your information from. That's what we mean by top sources. And they could still, you'll notice that this adds up to way more than the 100 because they could say as many as they wanted. Very few people said more than 2 or 3. So not surprising since we're, these are all coming from, I don't know, college kids in some kind of class. 60% go, man, I go straight to a Google search, which frankly I do too. Right? So it's not an unsurprising thing. The thing that's so striking is the red bar next to it when they also say for 60% of them also go to a Google search for class assignments. Right? The only 2 that are higher than that is I go to my professor, and that could be, they're not talking to their professor, they're using notes, hints, all of that, and then the textbook. But Google is, I go textbook, maybe, and again, this is if they buy the textbook, let's be really honest, and we have plenty of data. I have lots of data from textbook publishers telling me how many kids don't buy the textbook because it's expensive and they don't open it, so why bother? Their teacher, their TA, and Google search is number 3. Right. So very good. But then on the other hand, when you look at Science for Their Own Knowledge, they are self-reporting again, self-report that they go to both professors, right? They go to their lecture, maybe, and they're going to online science sites. So that would be like NASA sites, different mission sites and things like that. Social media.
I want to point out that blogs is at the bottom to my fellow science bloggers because this just breaks my heart.
Although I will say that, when we interviewed, right, sometimes your blog gets mushed into the online science sites.
That might be, I mean, a lot of blogs are Discover or something like that, so that's probably considered an online science site.
Right. So, that's we did do interviews, right? Because of course somebody should say to me, "Oh, well, what's the validity of this?" Well, we actually sat down with 30 of them, 30 undergrads to really have an in-depth conversation about what they meant by all of this, and that's how we came up with our categories. These are not the exact categories that are on the survey, but it's too long to get onto a bar graph, right? So that's why we kind of lumped them. And so, I wouldn't be too discouraged about the blogs because I do think that a lot of them get wrapped up into you're an online science site. The big bad evil Wikipedia that everyone's always worried about isn't that much of a problem. What has become really an interesting issue, and NRC also just released a report, is how people use Google. And so interestingly enough, the way people are using Google that we found out when I was interviewing some people is that the idea of replicability has been fascinating, right? So what they do is they go into Google and they'll have a question. So maybe they want to know how many planets are in the solar system, and they'll Google it. And they'll tell me, well, once I converge on enough websites telling me the same answer, that is the right answer.
Yep.
Wow. We've conflated this idea of seeing the same result multiple times into their Google search. And it's interesting because this report that came out, I guess, almost a year ago now, really talks about how high school students equate research with Googling.
Yes. Okay, anecdote. A friend of mine, when we were in grad school, in astronomy grad school, I was talking to a friend, telling him what he did about research, and his friend was like, but why do you have to go to school to do research? You can just use Google. And he explained it to his friend as, we're the people that put things on the internet for you to Google. That was how we explained research.
Yeah, so this actually gets me to my last 2 slides, and then... So slide 6, one of the things we also asked, and again, these undergrads, is we said, okay, so you told us where you get information from. Go ahead and rate the reliability of different sources, and give us your top 3. What do you think your top 3 are? And so all the scientists took a deep sigh and said, oh, thank goodness, journals and researchers are the most reliable. But of course we know you can't really get to them because they sit in universities and behind expensive paywalls and things like that. Textbooks, they feel pretty good about textbooks. Okay, but let's all remember textbooks come from textbook publishing. And number 3, info from their teachers. Phew, everybody was good. But then it got really interesting, right? Look at the next 2. Online science sites, great. And then the big drop, multiple websites. And so, frankly, I will tell you, all the information in the top 1, 2, 3, 4, really uninteresting, right? It's all things that we would expect. Where I've been able to do a lot of interesting research is everything else, right? Multiple websites, Wikipedia, YouTube, social media sites, family members. And so if you go to the next table. I'll show you what I'm talking about. What we started to do is, if you remember way back in the conversation, we were talking about having people say, what does it mean to study something scientifically? And we went ahead and rated them. 0 would be, you just didn't even try. Right? You said, like, science is boring. I don't know. It was just, like, not even helpful. 1 might be you started putting some fancy words like hypothesis out there. All the way up to 4 would be an exemplary response. Now, this is a subsample of my larger population. This was taken of a sample of 400 students. And what we did is we started to correlate where they, what they said was reliable, right, versus what kind of quality response code they got, and using that as a proxy of their science literacy. And again, small sample we're looking at here of only 400 people, but when you look, the people, or it didn't matter if you said professors, textbooks, and researchers were reliable, you were across the board, although that eked you into like the 3s and 4s on the quality. Online science sites did really great, so those NASA and those great blogs, but then the people who did online searches, good typo there, and Wikipedia, right, they could not get anything above a 2. And 2 would be saying, use evidence to test hypothesis. That's a level of a 2. Right. And so again, it's not really strong. We are collecting more data on this, but it was interesting. We started looking at these trends to say people who use online searches as the most reliable, and this had to be, they said it was the most reliable, just don't do well when they're describing science.
That's impressive.
So we kind of got excited. That got us into, we started making crazy claims, which I can't fully back up with evidence, so I'm really careful about it. But, you know, it just made me go, you know, information literacy is so important. So it goes back to if you're going to Google stuff, that's great. We all Google stuff, all academics, right? We all go to Wikipedia. But the point is that you understand what a reliable sources. Do you know what's reasonable? Those are the types of things that we're thinking about. And if our students are no longer buying textbooks and getting a lot of their information from my lecture, right, and I'm fallible, right, things come out of my mouth and we all make mistakes. Yes. And Google, we all want to think about how can we instill ways of thinking with our students to help them really make informed decisions. Now, for those of you who teach science majors and pre-meds, which I have been in the pre-med teaching track, and that terrifies me now. The bar is set even higher, right? Because now I don't need them to be able to make decisions about climate change, but now I need them to make decisions about like prescriptions, and so it's a whole new game which we haven't gotten into about, you know, content knowledge and science literacy of our majors, which is I think now into the can you do science? Are you good at science? Do you really understand what is scientific in a much more robust and high-stakes kind of way?
Yeah. We have a comment from Guido Bieber that is connected to this. He says, for him, Google is not the answer. Google is a tool to find answers. I see Google as a huge library, but as in every library, there are good books and bad books about a subject. It's up to everyone to be able to distinguish between them, and I think that gets right at the heart of what you were saying in terms of information literacy, being able to look up the answer, because I mean we have to look up the answers to things, political decisions, you know, policy decisions, and we're science and education people. That's completely outside our scope. We have to use that information literacy as well.
Yeah, but I think that what a fantastic comment. I think that's just a really great analogy. So.
Awesome. and Nancy Graziano quotes, "If it's on the internet, it must be true."
Right.
That is a joke coming from the fact that I don't know if this is still the case, but there earlier in the days of the internet, that was kind of a thing. Was like, well, it has to be true if they published it, you know, the understanding that anyone could put anything on the internet.
Yeah, it had a different meaning from, you know, peer-reviewed publication. So,
right.
Yeah.
Well, you know, the newest, you know, getting to the nerdydom of online journals now, the newest discussion of researchers is, you know, how do we deal with all these open access journals? Because I will tell you, you know, in my field, in science education, we have several journals of reputable organizations that are now going online. And, you know, there had been this review of the online journals of this year saying, you know, some of them were shady, and even as academics, looking at academic papers, trying to figure out, okay, is this reputable? And I think, you know, in my master's classes, they go, how do I tell if a journal is a good journal? So it's not even just for our students, it's for us as professionals to be able to look at scientific data. And it's just, wow, it's really complex. It's an amazingly complex issue. So
yeah, it is. And that evaluation is really hard. You know, it takes a lot of thinking and sometimes even a lot of background knowledge. So, you know, we expect that of people, but it's not an easy thing to expect when, you know, people in the profession have trouble doing it. And then yet we want people to be able to go and bring up a whole bunch of sites on Google, right, and then somehow be able to figure out, you know, okay, where's the best one, you know, which is a reliable site. It's not an easy thing at all.
You have to not just believe something because someone seems to be coming from a position of authority, but you can't know everything yourself, and you have to figure out what sources are the ones you can trust.
Yeah, and I think, you know, the other thing that's really interesting, and we didn't talk very much about it, is, you know, all the research on belief, right? And once you have it in your mind, you know, beliefs are impossible to change. It's one of those things, and I always get such discouraged Astronomy Astro 101 teachers when I go, you know, don't attack beliefs, because that is one thing that we know are very robust. So whether it is a belief in creationism, evolution, climate change, God, any of that, you know, all you can do is present evidence and try and help students become informed thinkers. But, you know, if you're Googling and you see stuff that resonates, that's your thing, you know. And
it is, yeah. And so it makes it so fascinating.
Even beyond beliefs, to things that you're not personally connected to, like misconceptions about, you know, that the seasons are, you know, the misconception that seasons are caused by the distance from the Earth to the Sun. Mm-hmm. You can talk about it. That's not the case. You can show models. That it in a way, I mean, it's not a belief they're personally attached to, I don't think, but that is one that's really hard to break. Misconceptions like that are really, just those ideas are really hard to break.
That's right. I mean, that's people's knowledge, right? It's your core knowledge that you know and you have known your whole life. And I mean, that's all that research that was done, you know, I mean, A Private Universe is a perfect example from Phil Sadler's group. I mean, that's the classic thing where, right, it's not even an issue because it is so ingrained in your mind. And we talk about things like preprims, like just, right, I mean, things that you just know in your whole life. If I get closer to the stove, it's hotter. So getting closer to the sun makes it hotter.
Yeah, makes perfect sense.
The newest crop of astronomy ambassadors for AAS and ASP are right now doing their first assignment, which involves watching A Private Universe. And so they're reflecting on that. And I remember thinking, oh gosh, this was when was that made, in the 80s? I feel like there was a lot of big hair.
Oh, big hair. Yeah.
80s, early 90s. There's a lot of big hair. Yeah, it was Harvard graduates. Explaining where the seasons come from, and a lot of them thought it was, you know, distance. It has nothing to do with intelligence. It's that ingrained feeling, and we all know what that's like when something that's been ingrained, like, dawns on you that is not correct, and it's just this. It's a really odd, disconcerting feeling when you realize it.
It is, because it's part of your identity, and there's a lot of emotion involved, and it's the same thing with beliefs too. It's really a part of who you are, and it's not a simple or a pleasant thing, really, to confront that and move beyond it. So,
but that's actually probably a really good parallel to science literacy, because if we look, people have been able to replicate the Private Universe, I'll call it an experiment, right, today. Jay Leno does this all the time. He walks out and he goes out and he talks to people and he goes, oh, wow, what are seasons? And we know, and so knowing that that is flat in the population, right, gosh, we've tried all of these standards and we've tried lots of changes in curriculum, and still we could say, you know, certainly there are many students who have improved, but across the population there are still those understandings that persist. And so, you know, education is tough, and you know, especially what we're asking teachers to teach, so much content, and it's unclear, right, with the new standards. The focus now is on these practices, which we all hope will help students with their science literacy, because now they have more understandings about practices, but it's yet to be seen, right, what that's going to look like, how that gets implemented, how much more pressure we put on these educators who are working so hard already. And so it's just, it's hard in this country to think about how we improve that.
Right.
I think about that at 8 a.m. twice a week. I have a class full of elementary education majors, and I'm teaching them a science content course.
Yeah.
I mean, this was designed before NGSS, but it's a lot of hands-on inquiry learning. that we're trying to get them to do, both for their own knowledge and then to pass on to their students. And it's tough because they come in, some of them flat out hate science, right? They tell me right in the big early survey, I hate science. And to get that knowledge and that process of science across in one semester is quite tricky.
It really highlights, I think, how difficult the question is. What do we want people to know? If you're just looking at content, how can you choose, 1 or even 20 questions that people will, answer, and then that will define if they're scientifically literate or not? Because think of all the things out there that there are to know. So you shift back and forth between, should it just be the processes or the practices, and don't worry so much about content, but people aren't comfortable with that because we feel like you should know some stuff, right? You should know what's going on with the solar system. It's critical, to your existence as a human being or something. But that's gets into cultures and what do we as a society feel that it's important for everybody to know. And that question, that'll never be answered.
I've got some of the most heated debates I've let myself get into on the internet. I don't let myself get into them often. Was about that issue, is whether or not our standards are moving away from having too much information or toward things like that. So
we'll see. Keeps going.
It's a big open question. I wanted to get to one more question from Elad. If you think about popular science series, things like Cosmos, either the original or the new one, do you think that aids science literacy, or do we have any data that aids science literacy, or does it not affect it at all? Is that reaching kind of other things? Where's that pop science media affecting the general idea of science in the public?
That is a fascinating question because, boy, Discovery Channel would love to have data on that. The answer in this, I have no evidence to support this. I think that things like Cosmos, and especially, the popular media really is helping us for support for science because, every time Neil gets up there and has this fantastic evening program, people are really inspired for astronomy and they're inspired to explore more. And I have seen some on that, but I don't really think that it's impacting as much our science literacy. And I think it goes back to just the issue that we know that a lot of these things are really hard to change, and without a really good foundation, that the programs are exciting and they're really engaging. And I love how many people had watched Cosmos this time around. But I'm not sure it's really impacting the education. And the interesting part about this, NSF's really interested in this, and that's why I said it's interesting, is that one of the calls that's coming out in 2 weeks, right, that we're all furiously writing for, is this advancing informal learning, right, so the ASIL. And it all has to do with something called free choice learning. A lot of people might call this informal learning, and so in the literature, a lot of people will use the folk definition of free choice learning, which means it's the kind of learning you do on your own time. It's a museum, it's television, it's on the internet, and you may walk away at any moment. And so we all scramble and wave our hands and do all these things to try and make you stay so that maybe we can eke out some learning while we're there. But we need to inspire you, and we need to make you happy and feel good about yourself and help your children. And so I would tell you we would love to have data that this media really has changed science literacy, but we don't have it. And the reason is it's methodological. Getting to the people who are watching the TV versus not is just a really big issue for assessment. Like, how do I find these individuals? And I'm sure somebody's looking to do a study. That would be a really fantastic study to put together. So,
yeah, how do you find the people that you didn't watch Cosmos? Tell me about science. Yeah, you have to.
Right. Now, I will tell you, someone like John Miller does do the science and engineering indicators. They do ask questions like that, right? They do ask, like, how often do you go to a museum? How often do you watch things on television? So they do have some self-reports on that. But there's some large money out there for people who can be clever enough to figure out how we use these informal, these free choice learning environments to increase science literacy. And now we might be looking at a family unit, right? Can we increase it for families and individuals at home and things like that?
Right. Yeah, really interesting.
Yeah, well, and of course the CosmoQuest, we're interested in that because you're coming to the website and helping us do science and watching our media completely by choice. I mean, unless you're here because your teacher has assigned understand it, because we've worked with your teachers. Yeah, there's that question of what's motivating you to come and what's motivating you to stay, and I know at least one, maybe a couple of you who are watching, I've interviewed on those topics, so we're looking into that, at least in our little sphere as well. Yeah. So, Sandlin, we're at the top of the hour. I don't want to keep you from important work and meetings and stuff. But thank you so much for coming on the show and talking with us about this really important topic. I always look forward to your talks at conferences every year because you guys are just expanding on this work.
Well, thanks for hanging out with us. This is fun, and I'm glad that we could share that. And anyone is always welcome to contact us if you have any questions. So.
How can they contact you guys? I know we put the link in the case, and I'll put it in there.
Yeah, and I'll just put my email in there as well.
So we'll get that.
I'm the only Sandlin Buxton on the internet, so it's not like I can hide.
I know. I'm the only Nicole Gugliucci on the internet. I totally understand.
That's amazing. That's hard to do these days.
Yeah. Awesome.
But the last thing to say is, of course, that our research is publicly funded, and so it is important to say that it is publicly funded, and so it has to be publicly available, and I think that we're always interested in public stakeholders. I mean, doing research just for research is silly. We want to do things that actually matter to people. So.
Yeah, and this is really important work, is getting to the heart of understanding of science. And if you're interested in this topic, I would recommend you go back to one of our earlier discussions that on Learning Space we had with Liz Neely and Emily Fink, where we talked a lot about the science communication side of this and the deficit model and why it works or doesn't work and when it doesn't work. So I think if you're watching this conversation and are interested in that topic, look back at our archives. I don't remember when it was, a few months back. We talked about the deficit model in science education because I think that might be a good good thing to pair with this particular episode. Yeah. So that's it for our show today. Friday, the Weekly Space Hangout is on. It'll be hosted by Fraser Kane. So hopefully I'll get to join. I've been away for a few weeks. That's one place that we hope is reputable for you to get your science news. To get it from us in the Weekly Space Hangout on Fridays. We'll talk about the week's top space stories. The failed Antares launch will probably be a big topic. That was sad. And then Monday is Astronomy Cast with Fraser and Pamela Gay. So check that out on our channel, on our YouTube page as part of our weekly Hangout series. So thank you again, Sandlin.
Sandlin, thank you. A lot of fun. Good topics.
Yes. And good luck on grant proposals as well.
Yeah.
Oh my gosh. All right, and thank you everybody for watching. See you next week.
Yeah, thanks everybody. Bye-bye. Always good. This is a natural for you.
Sure. It's so not. Hi everyone. Oh shoot, I hit the wrong thing. Awesome. Oh, there we go. Okay. Hi everyone. Welcome back to Learning Space. We apologize. We've had to miss a couple weeks. We've had travel and sick and grant writing. Last Wednesday was pretty intense, actually. Yeah, we were sitting in this room going type for an NSF deadline. So thank you guys for your patience and your support and your comments and messages and your understanding when we have to cancel last minute, even a couple weeks in a row. So thank you guys out there watching. Hi and welcome. Yes, we're in George's office today because my computer decided to completely flip out this morning, and so right now it's restoring from backup next door. So thank you, Georgia, for letting me take over.
Anytime.
Come in a frenzy and take over your computer. So with that introduction, we have a special guest with us, Sandlin Buxner. Welcome from University of Arizona.
Thank you.
Hey, Sandlin is a good friend of ours, colleague of ours. Does amazing work in science education research in teacher professional development, and probably a whole bunch of other things that I can't even think of off the top of my head at the moment. But that's the kind of stuff that we've worked on with you before. And I want to say hi to everybody. If you're watching this live, you can join the comments. We've already got comments for the, oh, I'm trying to read Nancy's.
Or I want them to have scientific thinking. And the person that a lot of us look to is John Miller. And John Miller is the person who was commissioned by the National Science Board, NSF, in the 70s to start looking at public science literacy. And he and a colleague started the science and engineering indicators of the public, and they started asking questions. And back in the day, right, back when we were all children, the kinds of questions were really basic questions. And so I have a graph, actually, that will help you understand the types of questions I'm talking about. So just on slide 1, these are facts, right? Declarative knowledge of things that they thought, gosh, if people knew the answer to these things, maybe they had a baseline of knowledge. And you may actually recognize them because, you know, when you're on Facebook and things, Pew Research will say, are you scientifically literate? And a lot of these questions overlap. And so, you know, things like right now, this might be really important, right? Antibiotics kill viruses as well as bacteria. Yeah. And it's one of those things where we want people to go, no, antibiotics are only good for bacteria, but not things like, oh, I don't know, Ebola. Right. There are some, you know, controversial type questions like humans evolved from an earlier species of animals. This, of course, is controversial if you don't believe in evolution, but is something that people really thought, gosh, if you'd gone to high school and really paid attention, you would know this. Plate tectonics, less controversial, although some. Then some more difficult questions like all radioactivity is man-made. Having people understand that it's not just a man-made problem, that there are a lot of radioactive materials that are good and natural, and if you took chemistry, you would understand this. You know, this one was in the news about a month ago. The Earth goes around the sun. Going back to, do people actually understand
comment? Oh, because it has a link in it. So using the Q&A app, if you look over here somewhere, it says click to join the Q&A. That lets you leave us comments and questions. And Michael says hi. And Nancy's in there, and I saw a couple of you guys. I apologize also for setting the wrong date for this. A whole bunch of people thought it was yesterday because I failed at date and calendars. No, it all worked out. It all worked out. That's what matters. So thank you guys for coming along. Be sure to ask any questions throughout our discussion. So, Sandlin, we invited you because we wanted to talk some about your research into science literacy. Can you start with a definition of science literacy? And then,
yeah, I know,
so
it's like a big topic, but I want no pressure. No pressure.
No pressure. No. Thank you for having me on. I am Stanley Buxner. I'm at the University of Arizona, and I work in a Department of Teaching, Learning, and Sociocultural Studies, but I also work in the Department of Astronomy, where I work with a professor, Chris Impey, and we have some wonderful undergrads who work with us, and we have been conducting studies of science literacy. And so one of the things that when we go and talk about this with researchers is we have to define what it is we're talking about. And for anyone who's ever read the newspaper, we throw the word around a lot. We say that science literacy is important to the American public, and it's more important to children, and it's important to not, the Ebola outbreak is all about science literacy. And even I work a lot with NASA, and NASA administrators say that science literacy is really important. But when you really try and press on what science literacy is, people start to break down because it's really hard. And so we get a lot of fuzzy ideas like, I want them to know things in science, or I want them to know how to do science. Understand that we are not an Earth-centric universe, and even though probably all of my college students truly believe that, they don't care, right? That they are the center of the universe. Truly understanding just basics of celestial mechanics and planetary motion and going, gosh, the sun is actually the center of our solar system, but not the center of the universe. And certainly the Earth goes around other things. The one that became really problematic is the second from the bottom, which is astrology is not at all scientific. This became really problematic for something we call a validity reason, that it was unclear from this question whether people understood the word astrology, if they truly meant, their horoscope, or if they were, all the others are ologies, biology, geology. So, even very well educated people call astronomy astrology. So this one got tossed. But back in the 80s, this was one of the predictors. If you didn't get this one right, you weren't considered scientifically literate, and they had to eliminate it when we really started looking at measurement issues. And then the last one.
There's two letters different, right? I mean,
right, exactly, it's the same thing. I've had PhDs go, "You're an astrologist," right?
Right.
And so we have to get at that in different ways, and some of the ways we've gotten at that, instead of asking about the word astrology, is we go, do you believe the motion of the planets affects your daily life? And all of that. And so so going back to what is science literacy, some people will define it as just some basic knowledge, right? The second piece that John Miller had started to look at was, could you describe what it meant to study something scientifically? And the way they do these surveys is they call people. So sometimes you'll be called. They call about 2,000 people a year, maybe every 2 years. And they'll just start talking to you, and they'll say, well, what do you think it means to study something scientifically? And they have this list of things they want to hear from you, right? Rigor, controls,